Hello friends, welcome to the tutorial on X-ray diffraction. In 1912, the German physicist von Laue reasoned that if crystals were composed of regularly spaced atoms, which might act as scattering centers for X-rays, and if X-rays were electromagnetic waves of wavelength about equal to the interatomic distance in crystals, then it should be possible to diffract X-rays by means of crystals. Under his direction, experiments to test this hypothesis were carried out. A crystal of copper sulfate was set up in the path of narrow beam of X-rays, and a photographic plate was arranged to record the presence of diffracted beams, if any. The very first experiment was successful and showed without doubt that X-rays were diffracted by the crystal out of the primary beam to form a pattern of spots on the photographic plate. These experiments proved at one and the same time the wave nature of X-rays and the periodicity of the arrangement of atoms within a crystal. W. H. Bragg and his son W. L. Bragg, only a young student during 1912, successfully analyzed the Laue experiment and was able to express the necessary conditions for diffraction in a somewhat simpler mathematical form than that used by von Laue. We'll dwell a little bit detail into the diffraction phenomenon exhibited by X-rays. A diffracted beam may be defined as a beam composed of a large number of scattered rays mutually reinforcing one another. Diffraction is, therefore, essentially a scattering phenomenon and not one involving any new kind of interaction between X-rays and atoms. Atoms scatter incident X-rays in all directions. In some of these directions, the scattered beams will be completely in phase and so reinforce each other to form diffracted beams. To quantitatively account the diffraction of X-rays by a crystal, let us consider rays 1 and 1a in the incident beam. They strike atom K and P in the first plane of atoms and are scattered in all directions. Only in the directions 1' and 1a' are these scattered beams completely in phase and so capable of reinforcing one another. They do so because the difference in their length of path between the wavefronts x and y is equal to qk minus pr equal to pk cos theta minus pk cos theta, which is equal to 0. Similarly, the rays scattered by all the atoms in the first plane in a direction parallel to 1' are in phase and add their contributions to the diffracted beam. This will be true of all the planes separately. It remains to find the condition for reinforcement of rays scattered by atoms in different planes. Rays 1 and 2 are scattered by atoms K and L, and the path difference for 1k1' and 2l2' is ml plus ln equal to d' sin theta plus d' sin theta. This is also the path difference for the overlapping rays scattered by S and P in the direction shown since in this direction there is no path difference between rays scattered by S and L or P and K. Scattered rays 1' and 2' will be completely in phase if this path difference is equal to a whole number n of wavelengths, or if n lambda equal to 2d' sine theta. This relation was first formulated by W. L. Bragg and is known as the Bragg law. Here n is called the order of reflection. It may take on any integral value consistent with sine theta not exceeding unity. It is equal to the number of wavelengths in the path difference between rays scattered by adjacent planes. Therefore, for fixed values of lambda and d', there may be several angles of incidence theta 1, theta 2, theta 3, etc. at which diffraction may occur corresponding to n equal to 1, 2, 3, etc. In a first order reflection n equal to 1 and the scattered rays 1' and 2' would differ in length of path and in phase by 1 wavelength, rays 1' and 3' by 2 wavelengths, rays 1' and 4' by 3 wavelengths, and so on throughout the crystal. The rays scattered by all the atoms in all the planes are therefore completely in phase and reinforce one another, and this is constructive interference to form a diffracted beam in the direction shown. In all other directions of space, the scattered beams are out of phase and annul one another, and this results in destructive interference. We'll now proceed to discuss on the instrumentation of a diffractometer. We have the Bragg equation n lambda equal to 2d' sine theta. Experimentally, the Bragg law can be applied in two ways. First, by using X-rays of non-wavelength lambda and measuring theta, we can determine the spacing d of various planes in a crystal. This is known as structure analysis or diffractometry. Alternatively, we can use a crystal with planes of non-spacing d and then measure theta and thus determine the wavelength lambda of the radiation used. This is known as X-ray spectroscopy. This figure shows the schematic of an X-ray diffractometer. A powder specimen C in the form of a flat plate is supported on a table H, which can be rotated about an axis O perpendicular to the plane of the drawing. The X-ray source is S. X-rays diverge from this source and are diffracted by the specimen to form a convergent diffracted beam which comes to a focus at the slit F and then enters to the counter G. A and B are special slits which define and collimate the incident and diffracted beams. The receiving slits and counter are supported on the carriage E, which may be rotated about the axis O and whose angular position 2 theta may be read on the graduated scale K. The supports E and H are mechanically coupled so that a rotation of the counter through 2x degrees is automatically accompanied by rotation of the specimen through x degrees. This coupling ensures that the angles of incidence on and reflection from the flat specimen will always be equal to one another and equal to half the total angle of diffraction, an arrangement necessary to preserve focusing conditions. In a diffraction camera, the intensity of a diffracted beam is measured through the amount of blackening it produces on a photographic film. A micrometer measurement of the film converts amount of blackening into X-ray intensity. In the diffractometer, the intensity of a diffracted beam is measured directly by an electronic counter. The counters convert incoming X-rays into surges or pulses of electric current in the circuit connected to the counter. This circuit counts the number of current pulses per unit of time, and this number is directly proportional to the intensity of the X-ray beam entering the counter. The diffraction methods. Diffraction can occur whenever the Bragg law n lambda equal to 2d dash sine theta is satisfied. This equation puts very stringent condition on lambda and theta for any given crystal. With monochromatic radiation, an arbitrary setting of a single crystal in a beam of X-rays will not, in general, produce any diffracted beams. Some way of satisfying the Bragg law must be devised, and this can be done by continuously varying either lambda or theta during the experiment. The ways in which these quantities are varied distinguish the three main diffraction methods. In the Laue method, we vary lambda and fix theta. In the second method, the rotating crystal method, we will fix lambda and vary theta in part. In the third method, which is the powder method, lambda is fixed whereas theta is variable. The Laue method. Laue method was the first diffraction method ever used. In this, a beam of white radiation, the continuous spectrum from an X-ray tube, is allowed to fall on a fixed single crystal. The Bragg angle theta is therefore fixed for every set of planes in the crystal. Each set picks out and diffracts that particular wavelength which satisfies the Bragg law for the particular values of d and theta involved. Each diffracted beam thus has a different wavelength. As you see in this slide, there are two variations of the Laue method depending on the relative positions of the source, crystal, and film. In each, the film is flat and placed perpendicular to the incident beam. In the first method, the transmission Laue method, which is the original Laue method, the film is placed behind the crystal so as to record the beams diffracted in the forward direction. This method is so called because the diffracted beams are partially transmitted through the crystal. In the back reflection Laue method, the film is placed between the crystal and the X-ray source, the incident beam passing through a hole in the film, and the beams diffracted in a backward direction are recorded. As we see in this figure, in the transmission method, the location of the Laue spots fall on ellipses. Here C indicates a crystal, F indicate the film, and ZA indicate the zone axis. And this figure shows the transmission Laue patterns of an aluminium crystal having cubic structure. In the case of back reflection method, the location of the Laue spots fall on hyperbolas. The third figure shows the back reflection Laue patterns of an aluminium crystal having cubical crystal structure. The white portion that you see over here is the hole that is set up on the photographic plate. In either method, the diffracted beams form an array of spots on the film. These spots are seen to lie on certain curves as shown by lines drawn on the photographs. These curves are generally ellipses or hyperbolas for transmission patterns and hyperbolas for back reflection patterns. The spots lying on any one curve are reflections from planes belonging to one zone. This is due to the fact that the Laue reflections from planes of a zone all lie on the surface of an imaginary cone whose axis is the zone axis. The rotating crystal method. In the rotating crystal method, a single crystal is mounted with one of its axes or some important crystallographic direction normal to a monochromatic X-ray beam. A cylindrical film is placed around it and the crystal is rotated about the chosen direction, the axis of the film coinciding with the axis of the rotation of the crystal. As the crystal rotates, a particular set of lattice planes will, for an instant, make the correct Bragg angle for reflection of the monochromatic incident beam, and at that instant, a reflected beam will be formed. The reflected beams are again located on imaginary cones, but now the cone axes coincide with the rotation axis. The result is that the spots on the film, when the film is laid out flat, lie on imaginary horizontal lines as shown in the figure. Since the crystal is rotated about only one axis, the Bragg angle does not take on all possible values between 0 degree and 90 degree for every set of planes. Not every set, therefore, is able to produce a diffracted beam. Sets perpendicular or almost perpendicular to the rotation axis are obvious examples. The chief use of rotating crystal method and its variation is in the determination of unknown crystal structures, and for this purpose, it is the most powerful tool the X-ray crystallographer has at his disposal. Finally, the powder method. Here, the crystal to be examined is reduced to a very fine powder and placed in a beam of monochromatic X-rays. Each particle of the powder is a tiny crystal oriented at random with respect to the incident beam. Just by chance, some of the particles will be correctly oriented so that their 100 planes, for example, can reflect the incident beam. Other particles will be correctly oriented for 110 reflections, and so on. The result is that every set of lattice planes will be capable of reflection. The mass of powder is equivalent, in fact, to a single crystal rotated, not about one axis, but about all possible axes. This figure shows the formation of a diffracted cone of radiation in the powder method. Let us consider one particular HKL reflection. One or more particles of powder will, by chance, be so oriented that the HKL planes make the correct Bragg angle for reflection, and in this figure, one plane in this set and the diffracted beam formed is shown. If this plane is now rotated about the incident beam as axis in such a way that theta is kept constant, then the reflected beam will travel over the surface of a cone as shown in the second figure, the axis of the cone coinciding with the transmitted beam. This rotation does not actually occur in the powder method, but the presence of a large number of crystal particles having all possible orientations is equivalent to this rotation, since among these particles there will be a certain fraction whose HKL planes make the right Bragg angle with the incident beam and which at the same time lie in all possible rotational positions about the axis of the incident beam. The HKL reflection from a stationary mass of powder thus has the form of a cone of diffracted radiation, and a separate cone is formed for each set of differently spaced lattice planes. The figure on the right shows 4 such cones and also illustrates the most common powder diffraction method. In this, also known as the Debye-Scherrer method, a narrow strip of film is curved into a short cylinder with the specimen placed on its axis, and the incident beam is directed at right angles to this axis. The cones of diffracted radiation intersect the cylindrical strip of film in lines, and when the strip is unrolled and laid out flat, the resulting pattern has the appearance of the one illustrated in figure B. Actual patterns produced by various metal powders are shown in the figure. The first figure is that of copper having FCC structure. The second one is that of tungsten having BCC structure, and the third one is that of zinc having HCP structure. Each diffraction line is made up of a large number of small spots, each from a separate crystal particle, the spots lying so close together that they appear as a continuous line. The lines are generally curved unless they occur exactly at 2 theta equal to 90 degree, when they will be straight. From the measured position of a given diffraction line on the film, theta can be determined, and knowing lambda, we can calculate the spacing d of the reflecting lattice planes which produced the line. Conversely, if the shape and size of the unit cell of the crystal are known, we can predict the position of all possible diffraction lines on the film. The Scherrer equation. The Scherrer equation is used to estimate the particle size of very small crystals from the measured width of their diffraction curves. Let us consider a crystal having thickness T measured in a direction perpendicular to a particular set of reflecting planes. Let there be m plus 1 planes in this set. We will regard the Bragg angle theta as a variable and call theta b the angle which exactly satisfies the Bragg law for the particular values of lambda and d involved, or lambda equal to 2d sine theta b. In the figure, rays A, D and M make exactly this angle theta b with the reflecting planes. Ray D dash scattered by the first plane below the surface is therefore one wavelength out of phase with A dash, and ray M dash scattered by the mth plane below the surface is M wavelengths out of phase with A dash. Therefore, at a diffraction angle 2 theta b, rays A dash, D dash, etc. to M dash are completely in phase and unite to form a diffracted beam of maximum amplitude, since the intensity is proportional to the square of the amplitude. When we consider incident rays that make Bragg angles only slightly different from theta b, we find that destructive interference is not complete. Ray B, for example, makes a slightly larger angle theta 1 such that ray L dash from the mth plane below the surface is m plus 1 wavelengths out of phase with B dash, the ray from the surface plane. This means that midway in the crystal there is a plane scattering a ray which is 1/2, actually an integer plus 1/2 wavelength out of phase with ray B dash from the surface plane. These rays cancel one another, and so do the other rays from similar pairs of planes throughout the crystal, the net effect being that rays scattered by the top half of the crystal annul those scattered by the bottom half. The intensity of the beam diffracted at an angle 2 theta 1 is therefore 0. It is also 0 at an angle 2 theta 2, where theta 2 is such that ray n dash from the mth plane below the surface is m minus 1 wavelengths out of phase with ray C dash from the surface plane. We have therefore found two limiting angles 2 theta 1 and 2 theta 2 at which the diffracted intensity must drop to 0. It follows that the diffracted intensity at angles near 2 theta b but not greater than 2 theta 1 or less than 2 theta 2 is not 0 but has a value intermediate between 0 and the maximum intensity of the beam diffracted at an angle 2 theta b. The curve of diffracted intensity versus 2 theta will thus have the form of figure A in contrast to figure B, which illustrates the hypothetical case of diffraction occurring only at the exact Bragg angle. The width of the diffraction curve of figure A increases as the thickness of the crystal decreases, because the angular range 2 theta 1 minus 2 theta 2 increases as m decreases. The width B is usually measured in radians at an intensity equal to half the maximum intensity, and B is equal to half 2 theta 1 minus 2 theta 2, which is equal to theta 1 minus theta 2. We now write path difference equations for these two angles for the entire thickness of the crystal rather than to the distance between adjacent planes. We have 2t sine theta 1 equal to m plus 1 lambda and 2t sine theta 2 equal to m minus 1 lambda. By subtraction, we find t sine theta 1 minus sine theta 2 equal to lambda. Or, using the relation for sine A minus sine B, we can write 2t cos theta 1 plus theta 2 divided by 2 sine theta 1 minus theta 2 divided by 2 equal to lambda. But theta 1 and theta 2 are both very nearly equal to theta b, so that we can write theta 1 plus theta 2 equal to 2 theta b approximately, and sine theta 1 minus theta 2 divided by 2 as equal to theta 1 minus theta 2 over 2 approximately. When we make this substitution, we have 2t cos theta b theta 1 minus theta 2 divided by 2 equal to lambda. When we substitute for b, which is theta 1 minus theta 2, we have t as equal to lambda over b cos theta b. A more exact treatment of the problem gives t as equal to 0.9 lambda over b cos theta b. And this equation is known as the Scherrer formula. And Scherrer formula is used to estimate the particle size of very small crystals from the measured width of their diffraction curves.